Hi everyone, and welcome to this video on hypothesis testing for the normal distribution. Now, before we get started, we've got to understand what these two words mean. Now, a population mean, we use the symbol mu, and a sample mean, we use the symbol X bar or capital X bar, depending on what we're using. For today, we're actually going to be using this one, so you won't see this at all. Now, population means everyone included. A sample mean is obviously a sample of the population, maybe 15, maybe 20, maybe 30 people are taken out into the sample. Now, you have to understand the parameters because as soon as they talk about a sample has been taken, you need to understand what the new parameters are. So let's say x is the random variable and that is distributed normally. You normally have the mean there and the variance here. Okay, but for a sample mean, a sample of the whole population, we say that is distributed normally still. And we're expecting the means to be the same, but it's the variance that is going to change. It's going to get less. It's going to get less because we're going to average it out for the size of the sample, which means if we have any extreme values in this sample, it's going to have less effect because it's being averaged out. Okay, you don't need to concern yourself too much, but what you do need to know is these two formulas. You already know this one hopefully, but you need to know this one off by heart and ready to use. Okay, so the only thing that changes in the sample mean is this value of n here. The variance is divided by n, and that is where it gets tricky. So here's a lovely question. Lots of text. You know you're in the deep end of stats when there's loads of text to read. So we've got a certain company is selling fruit juice in cartons. Now that is something we would expect to be normally distributed because it's quality controlled. Sometimes it'd be a little bit less, a little bit more, but there should be a normal distribution curve on something like that. And we're told that it has a normal distribution and it has a standard deviation of 3. So let's start by defining my random variable. So let x be the random variable. So amount of juice in, is it a carton? Yeah, it's a carton. So we can say x is distributed normally. We haven't got the mean yet, so if we read on we might see that, but at the moment we've got a standard deviation of 3, so we want the variance as our parameter, so we write it like that. We don't actually square it because in our calculations we're going to be using the standard deviation, so it's handy to write it this way. You could write 9, it wouldn't be wrong, but it's just not helpful for later. Now the company claims that the mean amount of juice per carton is 60, so now we have that in there. Okay, so we have the whole distribution model. So a trading inspector has received complaints that the company is overstating the mean amount of juice. Okay. And here's a sample, so you can see the word sample, so now you're thinking sample means, and our new type of distribution of 16 cartons, and okay, and he's got a mean lower. So we have to use a hypothesis test to see whether this is a valid claim that they are overstating, or it's just through chance, basically. So we need to write our null and our alternative hypotheses. Now, the null hypothesis is going to be that the population mean is 60, and the alternative one, well, they're saying that they're overstating, so that they're believing it's actually less than 60. So you can see this is a one-tailed test. So I'm going to just write this little heading here, reject HO if. Now I'm going to set this up exactly the same as we did our binomial. It's a good habit to get into, so then you can go between the two very easily. So I'm going to say probability that the variable in the sample mean is less than 59.1. Okay. Now, I actually haven't specified the model, so they're talking about sample mean, so I should have actually defined what this is. So the sample mean is distributed normally. The mean, the population mean, that stays the same, but now we have that, okay, but that is now the variance. So what we have to do is we have to square root that. Okay, that value there is the variance. So this is why it gets tricky. So 60. So if we type in that, oh, why have I put 9 there? It's just because I put 3 squared is 9. The sample size, your Wally, is 16. So if we work that out and square root it, we get 0.75. But we always have to write the variance because that's the parameter of a normal distribution. So we're working this out, 9 over 16, square root it, we're getting 3/4, and that is our standard deviation value that we need to. But we have to remember to square root this value to get the standard deviation. Right, so given that x bar is distributed normally, the population mean of 60 and a standard deviation of 0.75 or a variance of 0.75 squared. And that has to be less than or equal to 0.05. So we should be at this stage pretty used to writing a sentence like that, specifying the model. It's really handy because if you forget to do it here, there's a mark for it, but if you do it here, you can get that. So it's like a safety net, so please do write that. And we're going to draw a picture of the problem as well. So we're now looking at x bar, so it's important, again, I've noticed lots of you are not labeling this, so that the diagram is pretty useless without that label. We have a mean of 60, and we're looking at this value here, 59.1. So what is the probability of that happening? So we can use our calculator to do this. I'm going to use function 2. I'm going to put a lower of 0, the higher of 59.1, and you've got the two parameters here and here. So I meant to change colour there. Here and here. Just going to type that into my calculator, and that is equal to 0.1151. Okay, so what does that mean? Well, 0.1151, that's 11.51%. Okay, that's greater than 0.05. So therefore, there's insufficient evidence. Make sure I spell that right. To reject HO. Remembering, we reject HO if this data, this probability for this model is less than 5%. It's not, it's 11.51%. So therefore, insufficient evidence to suggest the volume of juice, I'm just going to have to make it a bit longer, is overstated. And there you go. There's a question. Let's have a look at another one. Oh, no. Where's all my other questions? Okay, here's one. So we'll go for this. So a machine produces tennis rackets with a mass of m grams where m is normally distributed. Okay, so they're kind of telling us that. It's a good habit to get into anyway. So I'm just going to say let m be the random variable mass of a racket. And m is distributed normally. So what do we have? Have we got the mean? Okay, no, that's the question. So this is good. So we have the mean, and we have a standard deviation of 1.2. And remember, you must write squared because we're writing the variance as one of the parameters. Now, part A, as soon as they ask you to find the mean, I'm thinking standard normal. So here's m. We don't know this, but we do know that 5% are in excess of 130. So if that's 130, we know that this bit here is 0.05. So as soon as we see an unknown, we've got to think standard normal, and underneath, directly underneath, it's always important to do that, we're going to draw our standard normal. So we need to work out how many standard deviations above the mean is 130. So for that I'm going to use my calculator. I'm going to use the inverse normal because I know the area of this is 0.05. Okay, so let's just pop that in, and I get 1.6449. That's to 4 decimal places. Okay, so we have a formula. So Z is equal to our score, which is 130. Take away the mean, which we don't know. In fact, I'm just going to change that Z, so I don't want to rewrite everything out. 1.6449 was our Z value, how many standard deviations above the mean. And we know the standard deviation as well. What are you doing, Wilson? 1.2. So rearrange all of this. You have to pop this on the other side because it's a negative term. You should get 128.026, and that goes on grams. And I'm going to store that on my calculator as A. So I'll write a little A there to just remind me where I've stored it. Okay, so in part B, it's saying 15 rackets are chosen. So now instantly I've got a discrete value. I'm thinking, well, this must be a binomial problem now. Find the probability that fewer than 2 of them are greater than 130. So the important thing to start off here is, do we have the probability for greater than 130? Yes, we do. It's there, 0.05. So B is all about a binomial. So we've got to change the variable. So let's let x be the random variable. We're going to say number of rackets greater than 130 grams. Okay, so x is distributed binomially this time, and we have a sample size of, what did they say, 15, and a probability of 0.05. And the question is, what is the probability that fewer than 2? Okay, well, if you go back to your binomial knowledge, less than 2 is the same as the probability of less than or equal to 1, because we want the probability of 0 and 1. So we can just use the cumulative distribution on your calculator for the binomial. It's option where you have to press down to get to that screen. It should be on the top of that screen. And when we type that in, we get 0.8290. Okay, that's to 4 decimal places. Okay, so that's part B done. Right. Part C, here we go, sample mean. So as soon as you see that, get in the habit of writing out your sample. So we know M is distributed normally for a mean of 128.026, that's stored as A, and a standard deviation of 1.2. Well, that means the sample mean is distributed normally. This bit stays the same, but then the variance is going to be divided by the sample size, and the sample size of 15 rackets still. Sometimes they can change that, you see. So that's the variance. So that is the same as saying M, the sample mean, is distributed normally, 128.026. But now what we need to do is square root this variance to get the standard deviation. And if you do that, you get 2 root 15, so I've just missed off the 1, over 25, and that squared is going to be the variance. Okay, so I've got that on my calculator. I'm going to store that as B. So I've got that as B, just write A again. So I'm going to use these in a minute, but it's handy if they're already stored so you don't have to type in anything. You're not going to lose any accuracy. Okay, so let's have a look at the question. A 5% significance level, so I know I'm using a hypothesis test, 5%. So we need to state our hypotheses. So null and alternative. So here we're saying the mean is 128.026. So let's read this text carefully. What is the other one? Is less than, okay? The mass of the racket is less than. So we're saying it is less than 128.026. So we're going to reject HO. That's a bad habit I've got into over the years. It's H0, it should be. If. So the probability of the sample mean is less than 127. That's because in the question it's telling us it was found to be 127. So is this result for this model takes a while to write it all out, doesn't it? Okay, so is this result for this model less than or equal to 0.05? Just check that again. Yeah, 5% significance level. So we've just got to work that out now. So if we draw the picture of the problem that we're dealing with, we've got a mean of 128.026. There's 127. We're expecting an answer less than 0.5, so always have that in the back of your mind. What is that probability? So I'm going to use the second function. I'm going to put a lower as 0, an upper of 127. I've got my standard deviation stored as B. I've got my mean stored as A. And when you work all of that out, you get a very small number, 0.000462. So therefore, there is now evidence to reject the null hypothesis. Therefore, there is evidence to suggest the mass is lower. Okay, so lower than the population. So we do these sample means to see if that sample is reflective of the population. In this case, it wasn't. Now, in your books, you'll see this formula here. You know, I don't really concern myself too much with that formula because before this was the standard deviation. So this is to standardize the sample mean, I should say. Now, I only use this again if I don't know the mean or the standard deviation, but this is just representing what the standard deviation is. So if you take your parameters and do it all properly, what I mean by that is go to this level here, don't stop here, go to this level here. That is your standard deviation. So at this point here, I would just be writing down what that standard deviation was. So I don't actually use this formula ever, but just the normal standardizing formula will be fine. Okay, one more question. So this time we have a machine producing bolts of D diameter. So let's just write that down. So let D be R dot V dot diameter of the bolts. D is distributed normally, and we've got a mean. That's nice, just got that straight off. And the standard deviation, super job. Remember to write the variance. So we've got a sample of 50 bolts. So talking about samples, I'm already thinking, right, I need to go sample means. Let's just do that now. So the sample mean is distributed normally. This is going to stay the same, but now we're going to go 0.015 squared. We're going to divide that variance by the sample size. And when we do that, this is now the variance. So this is the same as saying 0.580, square root this variance to type it all in, square root the variance to get your standard deviation, which I get something like 0.00212, and so we have to still write the variance, but that is what I need to be using. So I'm going to store that this time as A. It just overwrites what I had in there before because I don't want to keep typing that out. Okay, so, and here we go. This is the important bit. The diameter has changed from, okay, and the distribution after the service is still the same standard deviation. So that's important that we can just use the same model. Okay, and we've got a 1% significance level, and we're asked for a critical region. Right, so, oh, that's strange. So let's go for H naught. The mean is 0.580. The alternative, because they use the language as changed, it is not equal to 0.580, and we have a two-tailed test. So I'm going to say reject H naught if. So let's draw a picture of this one first, just so we all understand this one. So this is going to be d bar. We know this is 0.580, and we're looking for this value here. I'll call this one A, this one B, and we want a significance level of 1%. But because it's two-tail, remember you need to half that. So this is going to be 0.005, half a percent, and this is the same, 0.005. So we're going to reject H naught if something funny is going on here. The probability of d bar being less than a certain value, which we're unsure of, for this model, so 0.580, 0.00212, for that model has got to be less than 0.005. And we're also going to reject HO if it's greater than these values. We called that one B, so we'll mirror that. I'm just going to write all of this out again as quickly as I can. Okay, so for this model, and that also has to be less than or equal to 0.05 if we're going to reject HO. So this is just the inverse normal, so I'm going to put a lower of inverse normal, so we don't need to put lowers or uppers. So we put the area in that we want. That's easy to type in. We've got the standard deviation stored as A, so when you work this out, you get it to be 0.5745 to 4 dp. And this is the critical value, okay? This is this value here where we start to make our decisions. Now for this one, I'm not going to put this in. I'm going to put 1 minus that, because I can find all of this, and that will give me the same answer here. So for the inverse normal, I'm going to put 1 minus that in for the area. And when I do that, I get that value to be 0.5855 to 4 dp. And that is also my critical value. But it wants the critical region. Okay, so the critical region are d bar being less than 0.5745 and d bar being greater than 0.5855. Okay, so they're the critical regions. Anything in there, we're going to reject HO. So then in part B, they're telling us the mean diameter of the sample was actually 0.587. Okay, so 0.587, so this is part B here, well that you can see is bigger than the critical value, so it's in the critical region, so that's greater than 0.5855. There's a less than 0.5% chance of that happening, so therefore there's evidence to reject H naught. Therefore evidence to suggest, can't even remember what this question's on about, the bolts. So the bolts have changed diameter. Recalibration of the machinery is needed. Guys, it's a long video. Hope it all makes sense. Best of luck.